in a neighborhood close to the point of tangency, the tangent line gives values that are good approximations to the actual function values. This process of finding the tangent line and then using it to approximate a value is called linear approximation. And the function that we find is called the linearization of the function f at the value x equal to a. Today's lesson is on linearization and differentials. Linearization is the process of using the tangent line to approximate a value, and differentials is related to that, but just from a different perspective. On the screen, we see our goals. So let's just jump right in. Look at this image here. And what I want you to see is that on the left-hand side, we have the graph f of x equals 1 over x. And we're looking at the positive real numbers in the domain and looking at the value when x is equal to 2. Visually, you see this is the tangent line when x is equal to 2 to this function. And here's the equation of that tangent line. Now, let's look at a value that's close to 2. So for example, the value 2.1. So if we zoom in, remember the orange or the graph above is the f of x equals 1 over x, and then below is the tangent line. We'd like to get the value of f of 2.1, and we can approximate that value by the tangent line. And so here is the theory that in a neighborhood close to the point of tangency, you could think of neighborhood as this box here, but in a neighborhood close to the point of tangency, the tangent line gives values that are good approximations to the actual function values. And this is beneficial because the computing process to evaluate a linear equation is less than it is to process other types of equations like rational or multi-power polynomials. So if we can approximate something with a linear equation, that's going to save us computing time. So it's a big benefit. This process of finding the tangent line and then using it to approximate a value is called linear approximation, or you can call it the tangent line approximation. And the function that we find, this linear equation that is the tangent line, that function is called the linearization of the function f at the value x equal to a. So there's a lot of vocabulary there. The linear approximation, the tangent line approximation, and this function is called the linearization of f at, in this case, x equal to 2. So in order to do this, you're just going to compute tangent lines, and that's what's going to make it a little bit easy. So let us look at some examples. We're going to find the linearization of f at x equal to a. So here's our first example. F of x equals x plus x to the fourth at a equal to 0. In order to find the linearization, we're going to find the tangent line. So that means we need to find the derivative so we can find the tangent slope. F prime of x equals 1 plus 4x cubed. Then we're going to evaluate the derivative at the point 0. This is the tangent slope. Once we have the slope, we need a point. We already have the x coordinate for the point, so we need the y coordinate for the point. This is the y coordinate. So the tangent line, or the linearization, is the following function. Y equals, we have the tangent slope, x minus 0 plus 0, which is just y equals x. So this is the linearization, and that would be the function. If we were to look at, so let's grab a graph here. Okay. All right, if we were to look at f of x equals x plus x to the fourth power, and then we're going to graph the linearization, which is y equal to x, and then I zoom in here, you will see, let's get rid of the grid. Hiding this, that is what the function looks like, and then we can see that the linear equation y equals x is a good approximation in a neighborhood of 0. Now, how good? it actually is pretty good for a while. And then we can see where the function starts to curve, we have some separation. Still though, depending on our error values, we might be able to use this as approximation for values between negative, say 0.5 and maybe values up to negative 0. So that's the linearization. Let's do it again. The difficulty of this is really just the difficulty of finding the derivative, which is to say, if you've practiced finding your derivatives, then it doesn't have to be difficult at all. All right, let's do one that's trig. F of x equals sine x, a equals pi divided by 2. All right, we're going to find the derivative, which is cosine of x. Then we're going to evaluate the derivative at pi over 2, right? Cosine of pi over 2 is right here, and it's the x-coordinate, so that's 0. And this is the slope. All right, at this point, this lets us know this is the tangent slope, and this lets us know that we have a horizontal line. If the slope is 0, your tangent line is horizontal. That means the equation is going to just be y equals x. I'm sorry, y equals a value, not y equals x. Y equals a value, and we just need to find the y coordinate. So in order to find the y coordinate, we'll evaluate the sine at pi over 2. That's equal to 1. That's the y coordinate of the point. So when we put this together, the linearization is y equals 1. Now, I don't need to put it in point slope formula. I've already assessed that it is a horizontal tangent line. So let's look at that. So for this next example, we have f of x equal to sine x. And then I have the equation y equals 1. Now, remember we were looking at the point pi over 2. So let me highlight the point pi over 2 so that we can see it on the graph. And it will be the green point over here. There it is. Pi over 2, a little bit more than 1.57. So you see it's a little bit to the right of 1.5. This is the linearization. So if I were to zoom in a neighborhood of this value, you're going to see that red, it is still there, but it looks so horizontal. I'm going to hide that. Here is the sine. We know sine is curved, but in a neighborhood, it looks linear. There's the blue on top of it. It looks linear. And that is what the linearization is showing us. So now this neighborhood is smaller because the graph curves as much as it does. And so this would have a smaller neighborhood where this linearization is good for. However, this linearization is good for a neighborhood. Couple things to observe. Because of the periodic behavior of sine, this is the same linear equation you would get for every peak. So every tangent line would be y equals 1 at every peak, and that's interesting. Similarly, if we know that we're at a place where we're at the trough, we will have a tangent line that's y equal negative 1. And then in between, we would have different variations of tangent lines depending on what the slope values were. All right, let's do one more. And why don't we make it just a little bit harder algebraically, but, not too hard. Remember, you can have any type of function. That includes inverse functions, that includes logarithms, that includes exponentials. So let's do one that is an inverse trig. So what if we had f of x equals the arctangent at x equal to 1? The derivative of the arctangent is 1 divided by 1 plus x squared, or x squared plus 1. And then we're going to evaluate that at the value 1. So this is 1/2. This is the tangent slope. Now I need the y coordinate for the point. So remember what this means. This means what angle has tangent equal to 1, and it's in the domain of the range of the inverse, or the domain of this, and so the answer is pi over 4. Right, so this is the y coordinate. Right, so putting this together, we have the linearization is y equals, the slope is 1/2, x minus 1 close parentheses plus pi over 4. And if we want to simplify this any, it would just look like y equals, we could write x over 2, and then here we have minus 1/2 plus pi over 4. You don't have to get a common denominator. If you did get a common denominator, just be a little careful about your signs and how you combine it. But if I got a common denominator, I would probably write it like this: pi minus 2 divided by 4. But any of the ways, it's possible. All right, let's go back to Desmos and see what this looks like. All right, arctangent. And then the equation we had 1/2 parentheses 1, x minus 1 plus pi over 4. And then we were doing our point was at 1 and pi over 4. And there you go. There's what it looks like. So here is our coordinate point. Here the red is our arctangent, and we can see that the blue is a tangent line. And so the linearization just means that in this neighborhood, the linear equation is a good approximation. All right, so that's part 1. That's how you can find your linearizations. So now what we want to do is we want to use the linearization, meaning now that we know we can find it, how do we use it to approximate a value? Okay, so let's consider the following. Before I do that, let me just write a summary. So your linearization is just always going to be, if you need a more concrete formula, the linearization is equal to the slope at the point minus with the evaluation of the point. This is just point slope formula, but it's written in derivative notation. So if you're ever getting stuck, the linearization is equal to that. And sometimes people will identify the linearization with L of x. So this can be what you think about when you think of the linearization. It is just the function that is the tangent line, and you have the derivative for the slope, and then the point, which is evaluated at the function. All right, so in our next example, we want to actually test out the linearization and try using it. So we're going to approximate the value within 0.01. And let's look at this example. We have 1 divided by 0.98. Now, what we want to do is we want to identify an appropriate F, and we want to identify an A. So for this example, I can tell I have 1 over something, and it comes from practice, but this, I can identify that the F is equal to 1 over x, where I have subbed in this 0.98 for x. But I want a nice value for A, and so what I'm going to identify for A is a value that's close to 0.98, but easy to compute, and that's going to be 1. So identifying the structure and then identifying the value that is close, so there's just a small error. So given this, now I'm going to find the linearization. So the linearization, I'm going to take the derivative for the slope, so f prime of x. This is negative 1 over x squared. And then I'm going to evaluate this at 1, and that's going to give me negative 1. This is the tangent slope. For the y-coordinate, I'm going to plug it into the original function. So f of 1, and that's going to equal 1, and this is the y-coordinate. So the linearization is equal to tangent slope negative 1, x minus 1 plus 1. The linearization is equal to negative x plus 2. And so now what I'm going to do is I'm going to take that 0.98 and see, I'm going to plug it in. So this is the approximation. The approximation is plug in 0.98 into my linearization, and then my answer is going to be 1.02. So my approximation is 1.02, and that's what I think that's approximately equal to. And so now, given a calculator, I can compare and see how that holds up to what the true value is. 1 divided by 0.98 is the value 1.02 ... Let's get a copy of that. There we go. And we can see how close we are to this. We are actually within 10,000, so we're definitely within the 0.01 requirement. Okay. Different approximations could use different, types of values. Let's see. Let's do one more. Say I want to approximate. Sorry, let me number this. This was example 4, and now we're in example 5. Okay. The fourth root of 15.99. So this is some decimal because that's not a perfect square, right? And so what I need to identify is the best value that I can utilize for the best function and the best value. So when I look at this, I can identify the function as the fourth root of x, and then I can identify a as 16. Why 16? I know that 16 is a perfect fourth, so I know it's going to be a really nice result. And then 15.99 is close to 16. So I'll take the derivative of the fourth root. So that's going to be 1/4. And then when I subtract, I'll have x to the 3/4 power in the denominator. I'm going to evaluate the derivative at this value 16. So the fourth root of 16 is 2. 2 cubed is 8. This is 1 divided by 32. And you may or may not know your 30 seconds as a decimal, but that's a nice number. That's a really nice number. Now we're going to get the y coordinate. So the f evaluated as 16 is the fourth root of 16. That's 2. That's the y coordinate. This was the tangent slope. Now we're going to write our linearization. 1/32, and then x minus 16 plus 2. Right? X over 32, and then we'll have minus 1/2 plus 2, so that will be plus 3/2, 1.5, right? And then now we will plug in our approximation. We will plug in 15.99, right? And that would give us this value here. By the way, see, here's your 30 seconds with 0 through 125, right? So this is what we have as our approximation. And then here's what the actual, and remember, this decimal goes forever. We're only seeing the beginning of it. And so these are what the two values look like. So here's our approximation, and this is our true value. Right, so that's how we can use the linearization. All right, now we're going to talk about the differential aspect of it all. There's a picture that we need, so let's look at this picture so we can talk about the differentials. All right, so the differentials are going to give us this perspective of change in y, change in x. So you're going to see that delta y, delta x. But I want you to keep in mind slope. So the first thing, let me grab a highlighter. The first thing in the differentials is our definition. So in our definition, our differential dx, that is the definition of dy, of delta x. So we're going to always define the differential dx to equal delta x. Now, assuming that's true, there's a couple of things that you're going to see on this picture. First, let's just start with the actual function itself, which is blue now. So there are 2 points. There's this point A, and then there's this point close to it, and we're defining it by its level of closeness. So for example, if this were 2, this could be like 2 plus 0.01, which would be 2.01, right? Something really close. So that's how I want you to think about that. And then all we're saying up here is that that's just the F value that goes with that. So if that's 2.01, that's just the F value at 2.01, whatever that is, right? Now, that is what we call delta Y. That is actually the true change in Y, right? The true change in Y. This is really just like F of x2 minus F of x1, right? Put in a different perspective. When we are talking about the differential, then what we're talking about is how that true change is related to the slope. So the slope is F of x2 minus F of x1, and that will be the real slope through the 2 points. But we're looking at the slope of the tangent line, and remember the tangent line is a little different. So there's actually a different point, and that's when we look at this component that's called dy. And dy, okay, don't work too hard. Here's the summary of all that we're saying. Traditionally, delta y divided by delta x, right, which is f of x2 minus f of x1 divided by x2 minus x1. Hey, by the way, everybody, this is just slope. In the same slope you've always seen, traditionally, this is how we write slope. Now, we have the derivative now, and what we know is that then the slope of the tangent line is f prime of x. Okay, that's what we know. And when the tangent line is close, when your point is close to the function, this is what we're saying. We're saying that instead of this is approximately delta y over delta x. And then what we then are saying is that if we define dy equal to delta x, then f prime of x is equal to dy divided by dx, or said another way, dy is equal to f prime of x dx. So these are our 2 definitions from the perspective of differentials. The dy is going to be that change in x, but I said it backwards. Let me fix this. That's a dx. Apologize. The dx is going to be the change in x, but the dy is going to be the approximate change in y. And so dy approximates, let's come back up to the picture. You see this gap right here? That's the error from the approximation because it's not exact. But dy approximates delta y, and that is what differentials will tell us. So dy, and this is approximation for delta y, which is the true value. Okay, so really when we look at differentials, there's some picture you want to get your head around and some idea you want to get your head around, but it's this concept of a dy, a dx, a delta y, and a delta x. Delta y and delta x you should already be familiar with. It's just the dx and the dy that are new. And then here's the definitions. Dx is given, and then dy is the derivative times that dx. And this dy will approximate the true change in y, which is delta y. So let us look at some examples and do a differential. All right, alrighty. So first, let's just compute some differentials. All right, we're going to start with round 6. Y equals x cosine of x. So to find the differential is to find dy. And remember, dy is equal to the derivative times dx, and that's all you're going to do. So we need to take the derivative of this. That's going to be product rule. So 1 times cosine of x plus x times negative sine of x. All right, so now here's my answer. Dy will equal parentheses cosine of x minus x sine of x close parentheses times dx. That's what you do. You take your derivative and you multiply it by dx. The reason I need parentheses is because I need to multiply the entire function by dx. Right, let's do now an application where we're going to find the differential and we're going to evaluate it. All right, let's do y equal to 1 over x plus 1, and then we're going to do it at x equal to 1 and with a dx of 0.25. Differential still means the same thing. Dy is equal to the derivative times dx. Find the derivative. I can either use quotient rule or I can rewrite it and use chain rule. I'm going to just use quotient rule, and there's still a chain rule. Well, I'm just going to use quotient rule. So y prime will equal f prime g, that's just a 0, minus f g prime, that's 1, all over squared. So the derivative is negative 1 over x plus 1 squared. Okay, I'm going to evaluate, no I'm not, sorry. Now I'm going to write the differential. Okay, so dy will equal negative 1 parentheses x plus 1 squared, and then I'm going to multiply this by dx. That's it. That's my differential. And then now I want to evaluate my differential. Dy will equal negative 1. I'm plugging in a 1, so this is over 4. And then I'm multiplying by 0.25, which is another 1/4. So my answer is negative 1/8. And so that is the value of my differential. So what is this computing, right? What is this computing? This is computing. All right, let's look at a picture and talk about what this is computing. My function was 1 divided by x. Sorry. Here's my function. So what I just computed was negative 1/8. I'm just going to have this up here on the screen, right? That's what I computed. This is our dy. Now, this is an approximation of the true difference. The difference was from 1 to 1.25. So f of 1.25 minus f of 1. Let's go home screen, and then let's get some values up here so we can look at them. I have 1 comma f of 1 there. Right, so that's my point of tangency. Let's label it as that. Then, if we look back at the question, I have a differential of 1/4. And so what that means is, going back up to this picture, I am going to the right 0.25. So that's getting me to the point 1.25. Right, so that's why earlier when I said 1.25. So my next point, right, 1 plus 0.25, I mean, you see it, right? It's just 1.25. So here's my next point, 1.25 comma f of 1.25. Okay, and there's my a over here. Now, I have the tangent line. Here's the tangent line. There we go. Let's change the color. Let's make it 1.5. Actually, no, not 1.5. And let's make it black dashed. All right. So there's the tangent line. We see it. Boom, boom, boom. Okay. And then what the tangent line is doing is it is, let's call this L of X there. So then for the tangent line, L of 1.25 this is the value I'm getting. And so I could graph for you guys 1.25 comma 0.4375. All right. So here's what's happening. Here's the point of tangency, right? This red is the true value. This purple is what the tangent line is giving me as an approximation, right? This is what the tangent line is giving me as an approximation. And then what I have is, I have a typo. I have the wrong answer. I just realized, the whole time I'm like, this doesn't look like it's working out right. I multiplied wrong. That's my bad. This is 1/16. 4 times 4 is 16. There we go. 1/16. Get a black. Okay, and it's negative. Note the negative. All right. That's gonna look a lot better. So, all right, this is the true value. This is the approximate. Okay. So the true difference between the values is this right here. Right? This is the true difference. Let's move this one down. All right, this is the true difference between the two values. So this is what is known as, this is delta y. That's fine. Okay, that's delta y. dy was -1 divided by 16, which is this. And we can see how close they are. The true difference being -0.05 repeating, the approximate difference being -0.0625. So just short. That's what we're doing. And it's negative because if you look, you're going down. So the change in y is a downward change. That's indicative of the graph shape. It's a decreasing tangent. So we are going down and our number is larger because we're actually going down further. So our purple point is below the red point. So that's what we have found. When we found this value, we are approximating the true change, which is delta y. Right? It takes a while to get your head around. You're gonna really have to sit with the definitions and do some examples and sort through the ideas. But that is what you are doing, as simple as you take the derivative, you create the differential by the formula, and then you sub in for your x and your dx. It's the interpretation that you want to work on. All right, let's do another where we're looking at some geometric, situations. Okay. We're gonna find. We're gonna do both of these. So let's just go ahead and grab these as our last two examples. All right, we're going to find the change in volume and the change in surface area, where V is volume, A is surface area, again, according to this situation. So let us get to it. For our number 8 will be this number 78, and this will be our number 9. Find the change in volume, right? If the sides of a cube change from 10 to 10.1. So, volume cube, here's our equation. So the volume of a cube with respect to the sides is equal to x cubed. And then in this particular case, we have x equal to 10, and then we have dx equal to the difference from 10 to 10.1, so that's 0.1, right? So that's how that works. Identify your A, change in A, there we go. Now we're going to take the derivative or find the differential. So dv will equal 3x squared dx. right? So that's definition, that's the differential. And now we're going to evaluate. So dv equals 3, plug in 10, and then plug in 0.1, and that should equal 30. So the change in volume will be 30 units cubed. Remember, this is approximating the true change. And the true change will be, hey, well, what's the volume at 10.1? And then what's the volume at 10? And, right, what's that difference? So for us, we're approximating it as the difference is 30 units cubed. Notice this is positive, so this means an increase in volume, which we would expect, right? We expect an increase in volume, right? That's it. Now let's look at number 9. What about the surface area if the sides of a cube change from x to dx? So this is just arbitrary. So surface area of a cube is you have 6 faces and the area is all x squared. So you have 6x squared. And then again, this time we just have arbitrary a equal to x and then this dx. So the formula for us would just be the differential of a would equal 12x times dx. And then that would give you your change in area in units squared because it's area. And that's it. A couple of other things that text we talk about. Last thing is relative error. So relative error is just always whatever your function is, it's going to be delta f divided by f. So the change in the function value divided by the actual true value. And then the absolute error, I guess I should have did that first because that's just the change in the function value. So just keep in mind if you're thinking about differentials, you can approximate, right, df, and then you can approximate this by df over f. And then the percent error would be you take your relative error and change it into a percent, and you can approximate that in the same way like that. All right, have fun with differentials and linearization.